Chapter 7 Network Flow. In this chapter, we focus on a rich set of algorithmic problems that grow, in a sense, out of one of the original problems we formulated at the beginning of the course, bipartite matching. Recall the setup of the bipartite matching problem. A bipartite graph G equals to VE is an undirected graph whose node set can be partitioned as V equals to X union Y with the property that every edge little e in capital E has one end in X and the other end in Y. We often draw bipartite graphs as in figure 7.1, with the nodes in X in a column on the left, the nodes in Y in a column on the right, and each edge crossing from the left column to the right column. Now we've already seen the notion of matching at several points in the course. We've used the term to describe the collections of pairs over a set with the property that no element of the set appears in more than one pair. Think of man X matched the woman Y in the stable matching problem, or characters in the sequence alignment problem. In the case of a graph, the edges constitute pairs of nodes, and we consequently say that a matching in a graph G equals to V is a set of edges M, which is a subset equals to E, with the property that each node appears in at most one edge of M. A set of edges M is a perfect matching if every node appears in exactly one edge of M. Matchings in bipartite graphs can model situations in which objects are being assigned to other objects. We have seen a number of such situations in our earlier discussions of graphs and bipartite graphs. One natural example arises when the nodes in X represent jobs, the nodes in Y represent machines, and an edge xi,yj indicates that machine yj is capable of processing job xi. A perfect matching is, then, a way of assigning each job to a machine that can process it, with the property that each machine is assigned exactly one job. Bipartite graphs can represent many other relations that arise between two distinct sets of objects, such as the relation between customers and stores, or houses and nearby fire stations, and so forth. One of the oldest problems in combinatorial algorithms is that of determining the size of the largest matching in a bipartite graph G. As a special case, note that G has a perfect matching if and only if the size of X is equal to the size of Y and it has a matching of the size of X. This problem turns out to be solvable by an algorithm that runs in polynomial time, but the development of this algorithm needs ideas fundamentally different from the techniques that we've seen so far. Rather than developing the algorithm directly, we begin by formulating a general class of problems, network flow problems, that includes the bipartite matching problem as a special case. We then developed a polynomial time algorithm for a general problem, the maximum flow problem, and show how this provides an efficient algorithm for bipartite matching as well. While the initial motivation for network flow problems comes from the issue of traffic in the network, we will see that they have applications in a surprisingly diverse set of areas and lead to efficient algorithms, not just for bipartite matching, but for a host of other problems as well. 7.1 The maximum flow problem and the Fulkerson algorithm. The problem. One often uses graphs to model transportation networks whose edges carry some sort of traffic and whose nodes act as switches passing traffic between different edges. Consider, for example, a highway system in which the edges are highways and the nodes are interchanges, or a computer network in which the edges are links that can carry packets and the nodes are switches, or a fluid network in which edges are pipes that carry liquid and the nodes are junctures where pipes are plugged together. Network models of this type have several ingredients, capacities on the edges indicating how much they can carry, source nodes in the graph which generate traffic, sink or destination nodes in the graph which can absorb traffic as it arrives, and finally the traffic itself, which is transmitted across the edges. Flow networks will be considering graphs of this form, and we refer to the traffic as flow, an abstract entity that is generated at source nodes, transmitted across ages, and absorbed at sink nodes. Formally, we'll say that a flow network is a directed graph G equals to VE with the following features. Associated with each HE is a capacity, which is a non-negative number that we denote CE. There is a single source node S in V. There is a single sink node T in V. Nodes other than S and T will be called internal nodes. We will make two assumptions about the flow networks we deal with. First, that no H enters the source S and no H leaves the sink T. Second, that there is at least one H incident to each node, and third, that all capacities are integers. These assumptions make things cleaner to think about, and while they eliminate a few pathologies, they preserve essentially all the issues we want to think about. Figure 7.2 illustrates a flow network with 4 nodes and 5 edges, and a capacity value given next to each edge. Defining flow. Next, we define what it means for our network to carry traffic or flow. We say that an ST flow is a function f that maps each HE to a non-negative real number f, which maps from E to R+. The value f of E intuitively represents the amount of flow carried by HE. The flow f must satisfy the following two properties. 1. Capacity conditions. For each HE in E, we have 0 less than equals to f of E less than equals to CE. 2. Conservation conditions. For each node V other than S and T, we have the summations of f of E summing for OE into V is equals to the summations of f of E summing for OE out of V. Here, the summations of f of E summing for OE into V sums the flow value f of E over all edges entering node V, while the summations of f of E summing of OE out of V is the sum of flow values over all edges leaving node V. Thus, the flow on the edge cannot exceed the capacity of the edge. For every node other than the source and the sink, the amount of flow entering must equal the amount of flow leaving. The source has no entering edges by our assumption, but it is allowed to have a flow going out. In other words, it can generate flow. Symmetrically, the sink is allowed to have flow coming in, even though it has no edges leaving it. The value of a flow f, denoted V of f, is defined to be the amount of flow generated at the source. That is, V of f is equals to the summations of f of v summing for OE out of S. To make the notation more compact, we define f out of v equals to the summations of f of e summing for OE out of v, and f in of v is equals to the summations of f of e summing for OE into v. We can extend this to sets of vertices. If S, which is a subset or equals to v, we define f out of S is equals to the summations of f of e summing for OE out of S, and f in of S is equals to the summations of f of e summing for OE into S. In this terminology, the conservation condition for nodes V not in S or not in T becomes f in of V equals to f out of V. And we can write V of f equals to f out of S. The maximum flow problem. Given a flow network, a natural goal is to arrange the traffic so as to make as efficient use as possible of the available capacity. Thus, the basic algorithmic problem we will consider is the following. Given a flow network, find a flow of maximum possible value. As we think about designing algorithms for this problem, it's useful to consider how the structure of the flow network places upper bounds on the maximum value of an ST flow. Here is a basic obstacle to the existence of large flows. Suppose we divide the nodes of the graph into two sets, A and B, so that S is in A and T is in B, then intuitively any flow that goes from S to T must cross from A into B at some point and thereby use up some of the H capacity from A to B. This suggests that each such cut of the graph puts a bound on the maximum possible flow value. The maximum flow algorithm that we developed here will be entwined with a proof that the maximum flow value equals the minimal capacity of any such division, called the minimal cut. As a bonus, our algorithm will also compute the minimal cut. We will see that the problem of finding cuts of minimal capacity in a flow network turns out to be as valuable from the point of view of applications as that of finding a maximum flow. Designing the algorithm. Suppose that we wanted to find a maximum flow in a network. How should we go about doing this? It takes some testing out to decide that an approach such as dynamic programming doesn't seem to work. At least there is no algorithm known for the maximum flow problem that could really be viewed as naturally belonging to the dynamic programming paradigm. In the absence of other ideas, we could go back and think about simple greedy approaches to see where they break down. Suppose we start with a zero flow. F of z e equals to 0 for all e. Clearly, this respects the capacity and conservation conditions. The problem is that its value is 0. We now try to increase the value of f by pushing flow along the path from S to T up to the limits imposed by the H capacities. Thus, in figure 7.3, we might choose the path consisting of the H's, the set SU, UV, VT, and increase the flow on each of these H's to 20 and leave f of e equals to 0 for the other two. In this way, we still respect the capacity conditions, since we only set the flow as high as the H capacities would allow, and the conservation conditions, since when we increase flow on an H entering an internal node, we also increase it on an H leaving the node. Now the value of our flow is 20, and we can ask, is this the maximum possible for the graph in the figure? If we think about it, we see that the answer is no, since it is possible to construct a flow of value 30. The problem is that we are now stuck. There is no ST path on which we can directly push flow without exceeding some capacity, and yet we do not have a maximum flow. What we need is more general way of pushing flow from S to T, so that in a situation such as this, we have a way to increase the value of the current flow. Essentially, we would like to perform the following operation denoted by a dotted line in figure 7.3c. We push 10 units of flow along SV. This now results in too much flow coming into V, so we undo 10 units of flow on UV. This restores the conservation condition at V, but results in too little flow leaving U. So finally, we push 10 units of flow along UT, restoring the conservation condition at U. We now have a valid flow, and its value is 30. See figure 7.3, where the dark H's are carrying flow before the operation, and the dashed H's form the new kind of augmentation. This is a more general way of pushing flow. We can push forward on H's with the leftover capacity, and we can push backward on H's that are already carrying flow to divert it in a different direction. We now define the residual graph, which provides a systematic way to search for forward-backward operations such as this. The residual graph. Given a flow network G and a flow F on G, we define the residual graph GF of G with respect to F as follows. See figure 7.4. For the residual graph of the flow on figure 7.3, after pushing 20 units of flow along the path S, U, V, T, the node set of GF is the same as that of G. For each HE equals to UV of G on which f of E is less than CE, there are CE minus f of E leftover units of capacity on which we could try pushing flow forward. So we include the HE equals to UV in GF with a capacity of CE minus f of E. We will call agencies included this way forward agencies. For each HE equals to UV of G on which f of E is greater than 0, there are f of E units of flow that we can undo if we want to by pushing flow backward. So we include the HE prime equals to VU in GF with a capacity of f of E. Note that E prime has the same ends as E, but its direction is reversed. We will call agencies included this way backward agencies. This completes the definition of the residual graph GF. Note that each HE in G can give rise to one or two agencies in GF. If 0 is less than f of E less than CE, it results in both a forward H and a backward H being included in GF. Thus, GF has at most twice as many agencies as G. We will sometimes refer to the capacity of an H in the residual graph as the residual capacity to help distinguish it from the capacity of the corresponding H in the original flow network G. Augmenting paths in a residual graph. Now we wanted to make precise the way in which we push flow from S to T in GF. Let P be a simple ST path in GF. That is, P does not visit any node more than once. We define a bottleneck PF to be the minimal residual capacity of any H on P. With respect to the flow F, we now define the following operation: augment of FP, which yields a new flow F prime in G. Augment of f of P and P. Let B equals to bottleneck of PF. For each H UV in P, in such a path, if E is equals to UV is a forward H, then increase f of E in G by B, the bottleneck value, and else UV is a backward H and we let E equals to VU, and now decrease the f of E in G by B. Okay, after we finish the if-else block, and also if we finish checking all the agencies along the path P, after we break out the for loop, we return F. It was purely to be able to perform this operation that we defined the residual graph to reflect the importance of augment. One often refers to any ST path in the residual graph as an augmenting path. The result of augment of FP is a new flow F prime in G obtained by increasing and decreasing the flow values on agencies of P. Let us first verify that F prime is indeed a flow. 7.1 F prime is a flow in G. Proof: we must verify the capacity and the conservation conditions. Since F prime differs from F only on agencies of P, we need to check the capacity conditions only on these agencies. Thus, let UV be an edge of P. Informally, the capacity condition continues to hold because if E equals to UV is a forward H, we specifically avoided increasing the flow on E above CE. And if UV is a backward H arising from H equals to VU in E, we specifically avoided decreasing the flow on E below 0. More concretely, note that the bottleneck of PF is no larger than the residual capacity of UV. If E is equals to UV is a forward H, then its residual capacity is C minus F of E. Thus, we have 0 which is less than equals to F of E, which is less than equals to F of F prime of E, which is equals to F of E plus bottleneck of PF, which is less than equals to F of E plus by the definition of a bottleneck of PF, that is equals to CE minus F of E. So F of E plus CE, then minus F of E, which is equals to CE. So the capacity condition holds, that is 0 is less than equals to F of E, which is less than equals to F prime of E, which is less than equals to CE. If UV is a backward edge arising from H equals to VU in E, then its residual capacity is F of E. So we have that CE is greater than equals to F of E, which is greater than equals to F prime of E. And by the definition of the backward edge, that F prime of E is equals to F of E minus the bottleneck of PF, which is greater than or equals to F of E minus F of E, because F of E should be greater than or equals to the bottleneck of PF. So after F of E minus F of E, we get 0. And again, the capacity condition holds. We need to check the conservation condition at each internal node that lies on the path P. Let V be such a node. We can verify that the change in the amount of flow entering V is the same as the change in the amount of flow exiting V. Since F satisfied the conservation condition at V, so must F prime. Technically, there are 4 cases to check, depending on whether the H of P that enters V is a forward or a backward edge, and whether the H of P that exits V is a forward or backward edge. However, each of these cases is easily worked out, and we leave them to the reader. This augmentation operation captures the type of forward and backward pushing of a flow that we discussed earlier. Let's now consider the following algorithm to compute an ST flow in G. Okay, the name of the algorithm is called max flow. Initially, we set F of E equals to 0 for all h little e in G. While there is an ST path in the residual graph GF, let P be a simple ST path in GF, and let F prime equals to augment of Fp, update F to be F prime, update the residual graph GF to be GF prime. Then end while, after we break out from the while loop, we return F. We will call this the Fulkerson algorithm, after the 2 researchers who developed it in 1956. See figure 7.4 for a run of the algorithm. The Fulkerson algorithm is really quite simple. What is not at all clear is whether its central while loop terminates and whether the flow returned is a maximum flow. The answers to both of these questions turned out to be fairly subtle. Analyzing the algorithm, termination and running time. First, we consider some properties that the algorithm maintains by induction on the number of iterations of the while loop, relying on our assumption that all capacities are integers. 7.2. At every intermediate stage of the Fulkerson algorithm, the flow values, the set F of E, and the residual capacities in GF are integers. Proof. The statement is clearly true before any iterations of the while loop. Now suppose it is true after j iterations. Then, since all residual capacities in GF are integers, the value bottleneck of PF for the augmenting path found in iteration j plus 1 will be an integer. Thus, the flow F prime will have integer values, and hence, so will the capacities of the new residual graph. We can use this property to prove that the Fulkerson algorithm terminates. As at previous points in the book, we will look for a measure of progress that will imply termination. First, we show that the flow value strictly increases when we apply an augmentation. 7.3. Let F be a flow in G, and let P be a simple ST path in GF. Then V of F prime is equals to V of F plus bottleneck of PF. And since bottleneck of PF is greater than 0, we have V of F prime is greater than V of F. Proof. The first H E of P must be an H out of S in the residual graph GF, and since the path is simple, it does not visit S again. Since G has no edges entering S, the H E must be a forward edge. we increase the flow on this edge by bottleneck of Pf, and we do not change the flow on any other edge incident to S. Therefore, the value of f prime exceeds the value of f by bottleneck of Pf such a value. We need one more observation to prove termination. We need to be able to bound the maximum possible flow value. Here's one upper bound. If all the edges out of S could be completely saturated with flow, the value of the flow would be the summations of CE summing for all E out of S. Let C denote this sum. Thus, we have V of F, which is less than or equal to C, for all ST flows F. C may be a huge overestimate of the maximum value of a flow in G, but it's handy for us as a finite, simply stated bound. Using statement 7.3, we can now prove termination. 7.4. Suppose, as above, that all capacities in the flow network G are integers. Then the Fulkerson algorithm terminates in at most C iterations of the while loop. Proof. We noted above that no flow in G can have value greater than C due to the capacity condition on the edges leaving S. Now, by 7.3, the value of the flow maintained by the Fulkerson algorithm increases in each iteration. So, by 7.2, it increases by at least 1 in each iteration. Since it starts with the value 0 and it cannot go higher than C, the while loop in the Fulkerson algorithm can run for at most C iterations. Next, we consider the running time of the Fulkerson algorithm. Let n denote the number of nodes in G, and m denote the number of edges in G. We have assumed that all nodes have at least one incident edge, hence m is greater than or equals to n over 2, and so we can use big O of m plus n, which is equals to big O of m, to simplify the bounds, because m is greater than or equals to n over 2. 7.5. Suppose, as above, that all capacities in the flow network G are integers. Then the Fulkerson algorithm can be implemented to run in big O of m times C time. Proof. We know from 7.4 that the algorithm terminates in at most C iterations of the while loop. We therefore consider the amount of work involved in one iteration when the current flow is F. The residual graph GF has at most 2 m edges, since each edge of G gives rise to at most 2 edges in the residual graph. We will maintain GF using an adjacency list representation. We will have two linked lists for each node V, one containing the edges entering V and one containing the edges leaving V. To find an ST path in GF, we can use breadth first search or depth first search, which run in a big O of m plus n time by our assumption that m is greater than or equal to n over 2. Big O of m plus n is the same as the procedure augment of fp takes time. The procedure as the path p augment has at most m minus 1 takes. Given the new flow f prime, we can build the new residual graph in big O of m time. For each edge E of G, we construct the correct forward and backward edges in GF prime. A somewhat more efficient version of the algorithm would maintain the linked lists of edges in the residual graph GF as part of the augment procedure that changes the flow F via augmentation.